So last time we were talking about vertex cover. So for just to make sure that we all are on the same board, let's redefine the problem that we are interested in. Okay. And what we have been looked at. So first, input is a graph G. Question is, does G has a size at most k? And the parameter we were looking at was k, the solution size. Okay, so we had discussion about all kind of things, and we decided to design an algorithm with this parameter for some time. And as I said, we will only, up until now, we have only focused on vertex cover, and we will keep on focusing on vertex cover for time to come. Okay. Okay. So what did we see for this algorithm? Okay. So just to recap. So let's recap. Okay. First, we saw this nice enumeration algorithm, n choose k times n to the power big O of 1, right? Enumerate all subsets of size k and test. Okay, so this was our first algorithm that we saw. And then we decided that, okay, could we get an algorithm which is better than this? And the way we define better than this is that after a lot of discussion, we realized that any f of k n to the power big O of 1 time algorithm is better. Okay. And our first algorithm is direction was the following algorithm, if you recall correctly. Okay, so let's call this so we made a randomized algorithm. Okay, so what we made? We made a randomized, let's call it partition algorithm, or rather, let's say separation algorithm. Okay, let's give it a name. Okay, so what we made? A separation algorithm. Okay. So what was an observation? So the observation which led us to this result was the following. So what is an observation? If G has a vertex cover, if G has a minimal vertex cover S of size at most k, then there exists a set W such that A, W intersection S is empty, and B, N of W is equal to S, and C, cardinality of W is at most K, right? So this is a structural lemma that we prove, that if G has a minimal vertex cover S of size at most K, then there exists a set W such that A, W intersection S is phi, neighborhood of W equal to S, and C, cardinality of W is at most K. And the proof was fairly simple for this fact. Okay, so what was the proof for this fact? So the proof for this fact was that, okay, held by picture. Okay, so we said, suppose I do have an S, which is a minimal vertex cover of size at most K, then look at a set I, okay, which is an independent set. And now, since S is minimal, what property do have? Implies for all V in S, there exists a W in I, such that V comma W is in H, right? So basically what I'm saying that, look, if S is a minimal vertex cover, then for every vertex here, it must have an edge here, right? Or it must have a neighbor W in I. Why? Because if this would not have been the case, then suppose if we had a vertex here where which all the neighbors are here, then let's call this vertex X. Then notice S minus X is also a vertex cover, right? Contradicting that S is a minimal vertex cover. So what is the definition of minimal vertex cover? A vertex cover whose no proper subset is also a vertex cover. It's called a minimal. It may not be the minimum size, but you cannot remove anything from this and get a smaller vertex cover. So these kind of vertex cover are called minimal vertex cover. So because of minimality, what property do I have? For every vertex in S, there is a neighbor in W. Okay. So now, how do I constructed this W? So the construction of W was very simple. For every vertex, right, V in S, pick one of its neighbor in I, right? Now, clearly, for every vertex V in S, we have picked just one neighbor, right? Maybe for two different vertices, we could have picked up the same neighbor. Doesn't matter. But this implies that cardinality of W is at most K, right? In fact, so rather say this way, cardinality of W is at most S, which is at most K. Right? Now, what is the property of this W? First of all, where did I pick W? W is a subset of I, which implies W intersection S is empty. Secondly, what is the neighborhood of W? Where are neighbors of W? Look at this set of vertices, right? Where are their neighbors? They do not have any neighbor here because that is an independent set. So every neighbor of W is in S, right? So definitely this implies that N of W is contained inside S. Now, the way we have picked up for every vertex in S, I have picked up a neighbor in W, right? Which implies if I look at the neighborhood of that will cover this. So this implies that, in fact, by our construction, neighborhood of W is equal to S, right? So this was our structural lemma, right? And what was an algorithmic lemma? So algorithmic lemma was, so what was an algorithmic construction or algorithmic lemma is following. Okay. For any W prime, okay, for any W prime such that W prime intersection F is empty, first, and second, neighborhood of, okay, not, my bad. W prime is a subset of W. Oh. Okay, W is contained, we have that N of W prime is equal to S, right? So basically, if you look at the picture, what I'm saying to you is that, look at, this is my S, which is a vertex cover, and here is my set I, which is an independent set, and here is my set W, and what is the property of this? That neighborhood of W is equal to S. Now, you look at any other set, okay, which contains W, right? Look at this W prime, right? So where is the neighborhood of W prime? Because so definitely, what we know, that neighborhood of W is contained inside neighborhood of W prime, right? And which is contained inside S, but this is exactly equal to S, which implies neighborhood of W prime is exactly equal to S, right? Because we have shown that S is contained inside S. right? Because look, W is a subset of W prime. So W prime can only have more neighbors than S. But where are the neighbors of W prime? They are fully contained inside S because I is an independent set. So this is my algorithmic lemma. Okay. And how did we use for an algorithm? So we use this lemma for the algorithm as follows. Okay. Our algorithm was fairly simple after this. We said, do a random partition of my vertex set G into V1 and V2. What is the meaning of this? Toss a fair coin for each vertex. Toss a fair coin for each vertex, and if it is head, put this vertex in V1, else in V2. So this is what I mean by random partition of V2, of VG into V1 and V2. So for every vertex, I just toss a coin. If it comes head, I put him in the V1. If it comes tails, I put in the V2. Okay. And what is my algorithm? Say, check if n of V1, okay, is a vertex cover of size at most k. Okay. Now, what is the probability of success of this algorithm? So we said, okay, what is the success probability of this algorithm? Okay. So I said, what is the probability that S is a subset of V2 and W is a subset of V1? And now notice, because W and S are disjoint, I mean, this event can happen. So if you do maths, this comes out to be 1 over 2 to the power W times 1 over 2 to the power S, which is 1 over 4 to the power K. So with probability 1 to the power 4 power 1 by over 4 power K, we have the property that W is fully contained inside V1, S is fully contained inside V2, right? And then our algorithmic lemma proves the correctness that indeed n of V1 is equal to S, right? This is what we show. Because ultimately, what does V2 consist of? It consists of vertex cover and some independent set. Some other vertices are the independent set. So that's perfectly fine. Okay. So this is what we did last time. And then what was our algorithm? Our algorithm was, this is a polytime algorithm, right? This is an n to the power big O of 1 time algorithm with success probability 1 over 4 power K. Okay, 1 over 4 to the power K. Okay, okay. So, but in randomized algorithm, we need to make sure that the success probability is constant. So what did we do for this? We said, repeat the algorithm 4 to the power K, say n to the power big O of 1 times independently. Right? If success in any iteration say success, else return fail. Right? So basically what I'm going to do, I'm going to run this polynomial time algorithms not once, but I ran once. If I found an answer, I returned that answer. Else, I ran this algorithm all over again with again doing the same thing independently, and so on and so forth. If in any of the 4 to the power K poly n rounds, I succeeded in finding a vertex cover of size at most k, then I say, here it is a vertex cover of size at most k. If not, if I failed in each run of this algorithm, then I say fail. Now, what's a failure probability? So what is the probability that algorithm fails in every round? So probability that it fails in one round is okay. So what is the probability that it fails? Okay. So what is the probability that it fails in first round and second round and so on and so forth in 4 power k n to the power of big O of one round. So the first round that it fails probability is 1 minus 1 by 4 to the power k, right? And these are independent events in the sense, when I run my algorithm first time, it does not depend on when I run 10th time. Like I forgot everything and rerun this algorithm with new set of independent choices, which means the probability that it fails is upper bounded by 1 minus 1 by 4 to the power k to the power number of rounds I do. Okay. And if you do the maths and computation, this will come out to be this much. So what is the success probability? Is at least 1 minus 1 over into the power u and done. Okay. So this is my first randomized algorithm for vertex cover. Okay. So I have repeated what I have done up until now in the first 10-15 minutes. If anybody has any question, please ask.
So why don't we run like 4 to the power k many rounds? Why 4 to the power k into n to the power order of 1 million?
Oh, you could do 4 to the power k. This is still fine. I just did this just to even boost the probability beyond something. Like what I meant to say that by just running it in some polynomially many more rounds, so now you can bring the probability even closer to success probability as much closer to 1 as possible. That's it. There was no other motive. Is that fine?
Yes, it is correct.
Okay, good. Okay. Then I gave some homework, but I will come back to that homework a little bit later. Okay. Let's do some fun question. Okay. I'm going to call this a partition vertex cover. Okay. Let's do what I'm going to call a partition vertex cover. Okay. Some other form of vertex cover. Okay. Partition vertex cover. Okay. So what is a partition vertex cover? Here is an input, which is a graph G. Okay. And there is a function, which I'm going to call color or partition, whatever you want to call it. Function from Vj to 1 to dot third k. Okay. This is my function. And question, does G have a vertex cover that contains exactly one vertex of each color? Okay. Or so suppose, or rather, what it means is, suppose S is my vertex cover. What property do I want from him? I want that, look at, I can think of this, all those vertices, let's call the vertex V1, all those which has got, what is an F inverse of V1 is 1. All those vertices which has been assigned 1. What is V2? All those vertices which has been assigned 2. Basically, think that this function partition my vertex set into 1, 2, 3, k, right? Vg has been got 1, 2, 3. Okay. Oh, I think, oh, my bad. This is stupid. It is F inverse of 1. All those vertices which has been assigned 1, all those vertices which have been assigned 2. Right? So that gives you a partition, right? So every vertex has been assigned either 1, 2, or k. You assign them. And what I want a vertex cover that picks up one vertex from here, one vertex from here.
But this partition is not independent, right?
No, nothing. It's just some partition. Okay. This is what I call partition vertex cover. Okay. So what I have been given a graph and some partition I vertex it into V1, V2, Vk. And I say, hey, give me a vertex cover which picks up exactly one vertex from each part or each color class, however you want to say. So please let me know if you have understood the question. If you have understood the question, can you put +1 in the chat? Okay. My question to you is, okay, how many of you think this problem is NP-hard, and how many of you think this problem is polytype? Let's have vote. Okay, so my vote is partition vertex cover? Let me put that question in the chat. And is partition vertex cover in P and P complete? If you think in P, yes. If no, I give you a few minutes to think. So we think this is a polytime algorithm. At least he's not in majority, but who knows? Like all elections, there will be in last round, there will be lots of votes. So we are still counting the votes in a wrong reason. Okay. I'm not going to tell you an answer, but let's try to see what happens. Okay. Let's try to solve this problem in a fun way. Okay. Okay. Can we write, say, just vertex cover first? Okay. Forget about partition vertex cover. Vertex cover as kind of two-set formula, kind of two-set formula. Okay. So suppose I just wanted to write down that from every edge, at least some vertex should be picked. How can I write that? You get my point? All I wanted to look at a graph I wanted to write a two-set formula such that it should say, hey, if it is satisfiable, so what okay. I'm not talking about, I said, write a two-set formula such that if it is satisfiable, implies we have a vertex cover of G. I'm not talking about size. Please, important point, no size constraint. If it is satisfiable, it has some vertex cover of some size. I don't care. Okay. Can you write two-set formula like this?
For each edge, each vertex define a variable, and for each edge.
Yes, Sonak, I will come to you in a minute. But does everybody at least understand what two-set formulas are? Okay. Is anyone who does not know what two-set formulas are, that can put +1 or -1, let's say. If you do not know what two-set formulas are, can you put -1? Okay. So I assume that everybody knows what two-set formulas are. Okay, Sonak, carry on now. Okay. I just wanted to make sure that we are on the same, same plane. Okay. So now you please tell me, what are you trying to tell?
Yeah, for each vertex, define a variable.
And for each vertex, we define a variable. What is it called?
Say xv.
Xv. Very good. And for each variable, define it. So this is your variable sets. So basically, we have xv1, xv2, ... xvn corresponding to n vertices v1 to vn. Okay. Just to make life easier, let's denote our vertex set by let's say our vertex set is 1, 2, ... n. Or maybe not, it's fine. It's okay. It is a bit cumbersome, but let's find. Okay, now what do you want to say? This is your variables. Okay, and now what are my clauses?
Now make a clause cuv as xv or xu if and only if uv is an edge.
Suppose uv is an edge, and then you give a corresponding formula xu or xv. Am I right?
Yes.
Okay. So now, what is the formula with respect to the graph we made? It is basically and over edge uv in E, xu or xv. Is that fine with everybody? Okay. I want to say that G has a vertex cover if and only if phi of G is satisfiable. Am I right? Is this fine with everybody?
Yes.
I'm not talking about the size constraint. All I'm telling you that Sonak wrote a formula. I'm saying if I wanted to check whether a graph has a vertex cover or not, I could just test whether this two-set formula is satisfiable or not. Meaning, is there an assignments of variable at 0 and 1 so that every clause has at least 1, 1. Am I right? Okay. Anybody has any question here? If no questions, then please let me know by putting +1 if you have no question up until now. Okay, fine. Now, let's take this and let's ask ourselves, what kind of satisfying assignment do I demand to encode K size vertex cover? That's my question. Okay. But before I go to this, okay, I think I want to come to this question a little bit later. Okay, I'll come to this question later. Okay, first let's come here. Okay, you say if and only if phi g is satisfiable. Okay, so given, let's say, given an assignment, say alpha from xv1, xv2, dot, 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 xvn to 0 on, okay? Okay, and given an assignment, say alpha, further, say alpha is a satisfying assignment. For phi z, okay? Then how can we construct a vertex cover for G from alpha, right? So I gave you this satisfying assignment for this formula. And I said, yes, you said this if and only if, right? So what is in this proof of if and only if, given this assignment, which variables will correspond? Like, how will you construct a vertex cover? You understand my question? Right? I gave you this. I said, yes, phi j is satisfiable. And it is satisfiable because, hey, look at this assignment that satisfies it. Now, given these two things, how will you construct a vertex cover?
Since phi is satisfiable, therefore, at least one literal in every clause should be true.
No, so like that's the proof. But like, what is which set of vertices should I choose for vertex cover? What is my S?
The vertices
So,
are
which have
assigned
one.
to one by the assignment.
So
Yes.
what is S? Is V if alpha assigns XV to 1.
To one.
Do you agree? Now, all of you agree that S is indeed a vertex cover. Why? Because look at any clause, right? Look at any edge, right? It has a clause XU or XV, and one of those variables must have been set to 1. Otherwise, your phi g is not satisfiable, right? So it is indeed true that S is a vertex cover. Is that right? Okay, good. So now we know, and in the forward direction is also very obvious, given a vertex cover, all the vertices which is part of the vertex cover, you assign them 1, and every other variable, you assign them 0. And that's a satisfying assignment for phi g, right? So now we understand these two things. Okay. Now I want to say that, nah, I'm only looking for I want to find a satisfying assignment such that looking at this assignment, I should say it has a vertex cover of size at most k. Then what kind of satisfying assignment are you looking for?
Satisfying assignment with k variables 1 and others are 0.
Ajay Krishnan, do you agree with her? You are muted. Or at least I don't hear you. Okay, I'll come back to you. But at least I can't hear you, Ajay.
Shall I repeat?
No. I think everybody else. Do you hear what she said? She said, hey, don't look for any satisfying assignment. Look for satisfying assignment. Look for satisfying assignment that sets at most k variables to 1. Right? Definitely, if you have a vertex cover of size at most k, right? So now we can say, we can take this sentence, copy, right? And what can we write? G has a, let's say, let's put that, has a vertex cover of size at most k, if and only if phi g is satisfiable with an assignment that sets at most k variables to 1. Is this statement true? Is this statement fine for everybody? Right? If you have a vertex cover of size at most k, then clearly you set the vertices to 1 and rest to 0. That's a satisfying assignment. In the reverse direction, whatever proof you did, let S equal to all variables which is set to 1. I mean, that proof still goes through. So this is fine. Okay. So this leads to the following. Okay. And these are called, this has a name. Okay. This kind of assignment has name. This is called an assignment of weight at most k. What is it called? This is an assignment of weight at most k, because there are only k variables which are set to 1. Okay, so these are called assignment of weight at most k. Okay, all good? Okay, so now here is another question that comes. Okay, let's see if you can. Okay, min weight TwoSet. Okay, what is my input? Is a TwoSet formula phi. Okay, and what is the question? Does it have a satisfying assignment? Does it have a satisfying assignment of weight at most k? Now, this question for all of you people. Is min weight TwoSet in P or in PC? And this time I won't prove. Wait.
Just a question.
Wait, Shavani.
Okay.
Anybody else?
It is in NPC
Why?
because we just reduce vertex cover to min weight to set.
We just reduced because essentially this is a generalization of a vertex cover, right? Because in TwoSet formula, look, in fact, what we showed our reduction was to very different kind, what is called monotone TwoSet, right? It was monotone TwoSet, means there was no, like we never had X or Y bar. We never had such clauses. So, but TwoSet allows clauses with literal and its negation, right? So min weight TwoSet is much more general problem than vertex cover. So definitely it's NP complete, right? So, okay, so this is just a side remark, okay? Now let's go back to our partition vertex cover, okay? Okay, that is where we started, right? We wanted to understand the complexity of our partition vertex cover, right? And then we tried to do via SAT, but okay, and then we went around and came to this, okay? Okay. So my question is, okay, so let's go back to partition SAT. Okay. I know many of you might be thinking, where is my branching algorithm? Where is my pre-processing? They all will come. It is a time for it. But they're not coming soon. This much I can tell you. Okay. And It is on purpose done so that you show up to the class. Okay. 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 And so we try to, okay. So now I want to, so we started this partition vertex covered and we said, okay, let's make this phi G formula, which was nothing but and of u comma v in E, right? XU or XV, right? This definitely captures vertex cover. Okay. Now, how can I, like, let's call it, but this is just, this formula just captures vertex cover. Can we do something that it captures partitionness? You get my question? Can I add some more clauses and make sure that it captures partitionness? You understood my question? I basically, what I'm trying to tell you that, can I add more clauses and then say, hey, if it is satisfiable, then you have a partition vertex cover. Right? Just satisfiability testing, I want to say it has a partition vertex cover. Can you add more clauses? Okay. Let us focus on V1. Okay. What do you want to say in English? From V1, what do you want to select?
A vertex which must be a part of solution.
Yeah. Or in other word, what do you want to say? Or suppose I want to say I don't want to select two vertex from here. Then can you say something? Suppose
there cannot be an edge between.
No. Suppose I just want to say out of A and B, don't select both. Suppose I want to say this. Then what happens?
So we will create clauses such that A and B complement means negation of B.
Okay. So what she says is that do this. What is the meaning of this? Look.
No, I think XA
I don't
or
understand this.
Yeah, that's what.
negation of XB.
That's it. I think this is what it should be. It's like complement of this clause.
Or it should
You
be
can,
XA.
you can do, yeah, but like you can do de Morgan law and do this.
Okay.
I am not trying to do that, but like you can do de Morgan law and change it to whatever you wish. But what I'm trying to say, look at XA and XB. This event shouldn't happen together. Right?
Yes.
Okay. So suppose I add a clause, I add a bunch of clauses. Let's call it phi P of G, P1, or rather V1. What is this? This is and. So for all x1, x2 in V1, x1 not equal to x2, if I put x, oh, this is bad notations, my bad. V1, V2 in V1. This is also very bad notation. W1, W2, W1 not equal to W2, XW1 and XW2 complement. Okay, or rather, okay, so if you don't like what I wrote, okay, so fix XW1 and XW2. What are the possible things they can take. Both could be 0. Okay. I think this is not the right way of writing it. Okay. How do I write? No, this is fine. No, okay. I think that I was writing to write truth table for them. Okay. Both can take 0, 0. Right? Both can take 1, 1. It can take 1, 0, or I can take 0, 1. And all I want to say that, what does this tell you? This is not allowed. This is what this means. So what is allowed? So what is allowed? XW1 or XW2 is allowed. Okay? Right? And what else is allowed? XW1 is allowed or XW2 bar is allowed. Right? Okay. What else is allowed? XW1 bar or XW2 is allowed. Is this fine?
Yes.
Right? So I can replace this with all these 3 clauses. But this is just a two-set formula, no? Right? You understood what I wrote? Okay. Now, because of this, can you select 2 guys from this partition? Because if you select from the 2 guys, like 2 variables are set to 1, then you will have trouble with these clauses. These clauses cannot be satisfied. Right? These clauses cannot be satisfied. Okay. So let's write down our new phi tilde g is what? So I first do phi g, then I do and for all the, so it is and of phi v1 of g dot 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 and phi vk of g. This is what my phi tilde of g is. You got the formulas? Now I want to say G has a partitioned vertex covered if and only if, maybe we might have to add more thing, if and only if it's satisfiable. Right? Do you agree to this? But we have to prove this. But this is what I want to prove. Is any direction easy? If G has a partition vertex covered, you set those variables to 1 and rest to 0, right? So by definition, it is a vertex cover. And from every part, you have picked up 1. So all the clauses will be satisfied of types phi v1 of g, phi v2 of g. Because what is this encoding anyway? It just encodes that from v1, you can pick at most 1 vertex. This is what this set of clauses picks up. What is, okay. So what does this picks up? This, what do you call? What did I name I gave? Okay. This represents select at most 1 or set at most 1 variable to 1. Represents set at most 1 variable to 1. Do you agree? This is what it does. Right? This fact represents that from this set of variables, you are only going to represent at most 1 variable. Okay? Okay. Now, G has a partition vertex cover if and only if phi tilde of G is satisfiable. This is what I want to say. Okay? Okay. So forward direction is what? you picked up one vertex from each of this part, right? Now, because look at the clauses which comes from 5G, right? They are vertex cover clauses. If you have a vertex cover, then this phi of G is definitely satisfiable, right? So this does form a vertex cover, so this is satisfiable. Okay, and what does the partition guys tells us? That look at any pair of clauses, right? Look at any pair of clauses, right? If it does not involve this guy, if it does not involve this guy, then in each of them, there's one guy which is set to, there is one with bar, so that is set to 1. So that's perfectly valid.
So don't we have to add like another formulas like representing that from each partition we have to take at least one?
Maybe we'll get there, but all I'm saying, the forward direction is fine.
Yeah.
Okay.
Okay, I also have a question that you have written that we need to take at most one vertex from each partition. Should it not be exactly one?
No, I'm saying
That is
that
it.
what formula I wrote, it only represents this fact. I'm not saying that this is not job. I'm saying what piece of formula I wrote, it only represents the fact that from these set of variables, you can pick at most one variable. That's all that I'm saying. I'm not, look, I want something, but what I'm able to achieve, it's something. Right? And we'll get there. Okay. But all I'm saying, tell me from the formula which I wrote, can you tell me that you will definitely pick one variable from here? You understand my question? Right? I wrote a piece of formula which I'm able to tell you that at this point of time, at least the clauses and everything which I wrote, I'm only able to guarantee that this is what it is.
Okay.
Is that fine?
Yes.
Okay. Okay. But reverse direction, I can say, look at the set of guys which are set to 1. Right? Look at the set of guys, look at S such that V, okay, and alpha sets V to 1. What is the property of S? First of all, there are two properties. S picks at most one vertex from each class. Right? At most one vertex from each class because of the constraint. Plus, S is a vertex cover. Right? What I'm not able to guarantee? What I'm not able to guarantee from here? Tell me, what cannot I guarantee?
At least one vertex is selected.
Okay. We can't guarantee that we select at least one vertex from each class. Right? This I don't know. At least my formulas cannot guarantee this. You understand my point? At least I don't know how to do it. Do you think do you know any way to do this? Do you think you can add to my formulas and achieve this? How do I ensure that you pick at least one?
So instead of the 3 clauses, we just add 2 clauses.
What?
Exclude 0, 0.
Okay. Yeah, that's too much. If you exclude 0, 0, it just means that that is too much. Then you can't ensure that you will pick at most one. Because from whom are you going to do 0, 0?
We add one more new class
Yes.
for each class. If
Yeah.
just or of all the
Yeah.
vertices in that class.
Yeah. But that's
So
what
we
is the
need to
size of
start.
that? What's the size of that?
It will be the size of the class itself.
But that's not TwoSet formula, no?
Or TwoSet.
Okay. I have a constraint. Okay. Since I also don't know the answer, I'm going to change my question. Okay. So what I'm going to change my question? Here's my tell. The G has a vertex cover that contains, what should I change from exactly? Yes. At most one vertex of each color. Now my formula is fine. Right?
Saki.
Yes.
So for this reverse direction, even if we have exact,
Yes.
then for the remaining sets, we can take anything.
No, I didn't get your question, Pallavi.
So in the reverse direction proof, so our problem is that from some sets, we are not picking anything.
Yes.
Right? So
Okay.
from those sets, I can pick anything.
That's correct. She's also right. Okay. So at least, okay. So either we make at most, but even with exactly, we are happy. Why we are happy? Let's see. She's very right. So let's respect her and let's do exactly. So what happens? Did you realize what she said? Okay.
No, I didn't get her.
Look at S. S picks at most one vertex from each class, right? Okay. So suppose what I do, suppose S misses a vertex from class, say Vj, okay? Add an arbitrary vertex from Vj to S. Is that fine? Look, if from some class you miss any, just pick an arbitrary vertex from this. Now, new S selects exactly one vertex from each class. Do you agree to that? Is this construction fine? Hello?
Yes.
Right?
Could you just repeat this construction?
Look, what happened? So there's nothing. Suppose this is my class, okay? And in the beginning, I could only pick S from here, here, here. I don't have anything here. But notice that these red colored people does form a vertex cover. Is that fine?
Yes.
Sayani? Okay.
Yes. Yes.
So from the classes, like the first class, you did not pick anybody, right?
Mm-hmm.
Let's pick something.
But how do I pick something? Already
Just pick one vertex. Just pick any one vertex.
Okay.
Will that do anything?
Okay. That will also be a vertex cover.
Yes. So look, I'm not saying this will correspond to a satisfying. No, given a satisfying assignment to my formula, I can construct a vertex cover which picks exactly one vertex from each class. And this is how I will construct. Done.
Okay. Okay. Got it.
Okay. Okay. So now tell me, is partition vertex cover polynomial time solvable or partition vertex cover NP complete?
Polynomial time solvable.
So question. Is partition vertex cover P time or NP complete? How many of you think now it's polynomial time? And why? Those who knows, leave them. But let's see. I want to hear some younger people. So what did we do? So we basically, if you notice, gave a reduction from partition vertex cover polynomial time, right, to TwoSet. This is what we did. Do you agree?
Yes.
Now, what do we know about TwoSet? Does anybody know the status of TwoSet? How many of you know the status of TwoSet? If you know the status of TwoSet, put +1. Okay, excellent. And what is the status of TwoSet? This belongs to P. So what we showed? We gave via our reduction. Okay, so reduction is not only useful to show NP completeness. Reduction could also be used to show problem polytime. So what did we show? Partition vertex cover is in P as we can give reduction to TwoSet. Okay. That's all. Was it cute?
Yes.
Okay. But look, I'm teaching parameterized algorithm. So of course, I did not do it for this. Okay. Now, question. Could we reduce vertex cover to partition vertex cover? Natural. Okay. I'll do hint. Many of you know this trick. So let children think. Hint. When you can't think of anything, do random.
So in partition vertex cover, we get to choose the F, right?
Who is this? Omkar?
Pratik.
Is it Omkar?
It's Pratik.
Oh, hi, Pratik.
No, sir.
Yes, Pratik. So what are you saying, Pratik?
So I'm asking if
Yeah.
like, we
Yeah.
get to choose
Yes,
F.
you get to choose F. It's your choice.
to map everything to one.
Yeah, but that is a, does it reduces the partition vertex cover? If you solve partition vertex cover, you will get a vertex cover. Like, does it correctly does reduction to partition vertex cover if you just color them on? So what do you want? You want every, so let's ask ourselves, now, what is the meaning of reduction to partition vertex cover, right? Basically, suppose S is my vertex cover. right? What I want. So suppose it contains k vertices. What I want to do then? I want a function, f, that maps vertices in S to 1 to k, what? Injectively. Right? Like every vertex goes to different part. If I can come with an f so that every vertex in S goes to different part, then we are happy. Because then I have reduced my problem from vertex cover to a partition vertex cover. Right? And then I can solve the problem in polytype. Maybe, okay? So this is the kind of f we want. What I want, that every vertex in S gets to different part or gets different colors. No two vertex gets the same color. It becomes colorful. Right? Because then what happens if I can come up with such an f, whatever times it takes. So if I reduce, what is the meaning of vertex cover to reduction to partition vertex cover? It just means that, hey, if I find a solution to a partition vertex cover, I should be able to get a solution to my vertex cover problem. That is exactly what it means. It's if and only if. It may not be a polytime reduction because I'm trying to reduce an NP complete problem to a polytime problem. So, hey, you get my point? So, I should not be able to do this in, okay, this is, okay. I do not expect myself to, even if I do random, okay. So first of all, let's suppose I wanted to do deterministic time. Can it be polytime reduction?
No.
Could such a reduction running in p time exist? That's the first question. Let's understand these little things. Then we will worry about big things. First of all, can such a reduction running in p time exist? You're giving a reduction from an NP complete problem to a problem which you just now showed is in polytime. Can such a problem exist?
No.
Reduction. Then we'd automatically imply that P is equal to NP. We are done. Right? So we do not expect such a reduction to exist. Right? So we do not expect a reduction from an NP complete problem to a P time problem. But can there be reduction from a P time problem to NP complete problem?
Yes.
It always exists because P is contained inside NP. Which implies if a problem is NP complete, there is a polynomial time reduction from any problem in NP to me. Or the other way around, whatever it is. Okay, so we cannot expect a reduction from vertex cover to partition, but this is fine. But
so can't we like in the first randomized vertex cover we did two partitions. So here instead of like a fair coin, like take a fair k-sided coin and like partition k.
Excellent. This is what I want to do. Nothing more. That's all. I did two. I wanted you to think, let's do more. Exactly. Okay. So, okay. So hold that thought. Okay. Hold that thought for a minute. Okay. So let's ask him. So answer, all you people gave, answer was no. No such things. What about a reduction running in polytime, okay, with success probability 1 over poly in n? Is this possible? Can I come up with a reduction such that it runs in polynomial time and success is that at least 1 over poly n? say success probability is say for now with success probability say 1/3. Is this possible? What will happen? What great thing will happen if I do this? Then
we can solve the problem.
Then I can solve the vertex cover, which is an NP complete problem in polytime. With like we can get a randomized polytime algorithm for an NP complete problem. Okay, then that will imply some other kind of hierarchy collapse. So we don't expect. You get my point? Okay. We can't even have a success probability equal to 1/n to the power big of 1. We can't, because I can run this reduction several times independently, okay, and do some kind of democracy, like in the sense that choose the best answer from whichever, and you can reduce the probability to again constant. Don't expect it to happen, right? So the choices are that if we are giving a reduction from an NP complete problem to a polynomial time problem, either I take, so what is this? Either I take EXP time, FPT time, whatever you want to say, right? Time which is not polynomial. That's all that I want to say. Or success probability is like 1/EXP or 1/FPT, whatever. These things are allowed, but 1/poly success is not allowed. Right? So what is our assumption? So for NP complete problem, we do not even expect a randomized polynomial time algorithm. That is that's think of this way, that for NP complete problem, neither do we expect that it is a deterministic polynomial time algorithm. We do not even expect that it has a polynomial time algorithm or randomized polynomial time algorithm, a polynomial time algorithm with a constant success probability. We do not expect such algorithms. Is that clear to everybody? Okay. So this is a snippet which you should remember whenever you're making such reduction, because then when you are doing your algorithm, you can avoid these pitfalls to fall into. Okay. Okay. So now we will go back to Sonak, who said, well, let's do the following reduction. Let's do the following experiment. Okay. So what is our random experiment? Okay. Here's our random experiment. Assign every vertex 1 of 1 to k uniformly at random. Right? That's it. This is my polytime algorithm. For every vertex, I basically have. So basically, I assign a color I with probability 1/k. So think of this way, that I have a k faced coin. I have tossed it, where every number comes with probability 1/k, and whatever number comes, I assign to that vertex. This is what I do. So this is how we have computed f. So this is my f. That's it. This is my end of my algorithm. So how do I assign f? For every vertex, I toss this k faced coin. Whatever number comes, I assign f of that is this number. That's it. Okay. So construct it randomly. Okay. Now, what is the probability? So now, what is the probability that G, K, and now F is a valid instance of partition vertex cover? And what I mean by valid instance, like what I want to show now this, that G has a vertex cover of size at most k if and only if, okay, if and only if there exists partitioned vertex cover. Okay, let me PVC the wrong word. You will get confused. So partition vertex cover. What is the probability of this? So let's fix a set S. This is my set S, which is a vertex covered, say V1, V2, Vk. What is the probability of, let's say, V1 has got color 1, V2 has got color 2, and Vk has got colored k. What is the probability of this? Can someone tell me with this random experiment? What is the probability that f of V1 equal to 1 and f of V2 equal to 2 dot 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 f of Vk equal to k? What is the probability of this? Anybody?
1 by k to the power k.
K to the power k.
1 over
K power k.
right? Why does anybody say this? Can someone explain? I
For
told. Yes,
No.
Sonak?
Getting a colored f of v1 is equal to 1, f of v2 is equal to 2. These are all independent events.
Yes. And for each of them, we can get it with probability 1 over k. So 1 over k to the power k, right? Which is great for us, right? Question, can we boost this probability? Can we boost, like, can we say something better? Okay. For partition vertex cover, do you care that V1 gets 1 or V2 gets 2 or Vk gets k? Do you really care? What do you care? That these gets distinct colors, right? So you are also happy if V1 gets 2, V2 gets 1 and dot dot dot. So you are happy if any permutation of colors from 1 to k is given to the vertices in S. Any permutation of colors. Is that fine? Right? What is a good event? If our good event is that every vertex V1 to Vf as okay. So rather, let's say, what is the probability that F is injective, rather colorful on S? Okay. So look at V1, V2, Vk. How many choices of colors can we have? K. How many choices of color V2 has?
k minus 1.
Dot dot dot. So what is this? K factorial.
K factorial.
Right? So what is the probability that S is colorful or F is injective on S? What is the probability of this? Now please tell me.
K factorial upon k to the power k.
Of course. Those who are fine with this computation, can you put +1? Or I will do a bit more. Okay, fine. And what is this number? This is at least. Does anybody knows?
Was it 1 by e to the power k or something like that?
Yes, yes. This is, you're absolutely correct. This is 1 over e to the power k. Okay. So now what should be our algorithm? What should we do?
Repeat this e to the power k times.
Correct. Repeat the algorithm. How many times? E power
Okay.
times. And then what will be our success probability? Our failure probability is at most 1 over 1 e to the power k time in 1 over e power k time in 1 round. So how many rounds we did? E power k times, and each of them are independent, right? So the failure probability becomes So success probability becomes so what is the running time of this algorithm? What is the running time of this algorithm?
E to the power k times the running time of the partitioned vertex cover problem,
Which is some polynomial time. So what is this e to the power k number?
F of k.
Arey Baba, what is e value?
2.3 something 31.
Sonak, please check. This is just a base of what you call exponent. I think it should be something like 2.7 or something.
Yeah.
What is this?
2.73, I think.
Okay, doesn't matter. But this is, but like we should know. So now for vertex cover, we have made two algorithms. Okay, we had made two algorithms. One algorithm we made, first algorithm we made 4 to the power k n to the power big of 1 and constant success probability. Okay. Second algorithm we made is 2.7 3 to the power k n to the power big of 1 constant success probability. Hey, great. But up until now for vertex cover, we have not seen any deterministic algorithm. Okay. So let me see. Okay. So I will take a pause for a minute and I will ask all of you people, do you have any questions up until now? I am not going to give you name to any tools in my course this semester. Okay. I'm just going to teach you some algorithms. Okay. You will have to figure out what tools to apply as we go forward. Okay. I'm not going to name it. These are a bunch of methods to solve problems, right? So up until now, basically we gave reduction to polytime problem, right? First was what? You partition and then you look at its neighborhood. That activity was polytime activity, right? Second, we got a slightly faster algorithm, but then we had to work very hard in the sense that we had to solve some TwoSet instance, but we did give a reduction. So first we did some coloring, or we made the problem, like we broke the problem by doing some colorful experiment, and then resolve the problem using some polynomial time subroutines, right? So we were very successful. Okay. Now, before I leave for the day, I want to prove the lemma which I gave last time. Okay. So there was a suggestion from Sayani was that, hey, look at, so he says for deterministic algorithm, her suggestion was that why don't you look at a vertex of highest degree, and then we found an example which showed that this may not be the best choice to have. Okay. But then, okay, so now let's say, I can give you more randomized algorithms if you want, but let's leave it at 2 some other day. Okay. Moving towards deterministic algorithms. Okay. So here was an observation which we tried today. We said, let v1, v2 dot 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 vn be vertices of G such that degree of v1 is greater than or equal to degree of v2 dot 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 degree of vn. Okay, this is what we said. Okay, so this is a property. Then the observation was, or that we wanted, I wrote last time, there exists a vertex covered of if there exists a vertex cover of size k in G, then there exists a vertex cover S such that S intersection V1, V2 dot 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 vk plus 1 is not empty. Right? This is what we said. Am I right? Do all of you remember?
Yes.
Okay. Someone send me a proof which is correct. Okay. So that since this is a unique person, that should tell that person that who is it. So, but I don't want to tell name or something, but someone did send me an answer, and that unique person's answer was correct. Okay. Okay. So what do you think is the proof? Okay, we also assume that G does not have an isolated vertex. I don't think G has no isolated vertex. Okay, so this was one assumption. Okay, this is not an algorithm, it's just a graph theory, right? So this is what it say, that graph theory and algorithms, at least the way I have seen, they go hand in hand. But this statement is completely motivated from the algorithm I want to design, right? It's not that I'm just reading this for the structural purposes. No, it is a statement which is motivated from the algorithm I have in mind, or algorithm I would like to design. Okay. Anybody?
Sir, actually, if we name this set as sk plus 1, then if we look at the neighbor of sk plus 1, and that should be a subset of S, and so neighbor of sk plus 1, that size will be bounded by k, and every vertex.
Wait. What you were saying? That suppose this is, so what is your proof strategy, Somen? Like, go ahead.
Okay, so
you say let sk plus 1 equal to v1 to vk plus 1. Fine?
Yes. And then okay, let S intersection sk plus 1 equal to phi. I want to give some contradiction.
Suppose S intersection v1, v2, vk plus 1 is equal to phi. Okay, fine. Okay.
Then S should contain all the neighbors of this sk plus 1.
Then S, yes. Then, of course, then n.
Then so
of
neighbor of sk plus 1
is bounded by inside S.
Neighbor of sk plus 1 size will be bounded by k.
This implies that this is bounded by S, which is at most k. Yes.
Yes. Then, if we pick any vertex from sk plus neighbor of sk plus 1, that degree will be at most degree of vk plus 1.
I didn't get this.
So choose any vertex, say vj, from a neighbor of sk plus 1, n of sk plus 1. So degree of vj will be.
No, come again. Now, what do you want to pick?
Any vertex, say u from neighbor of sk plus 1.
Okay, so let u be in this. This is what you mean?
Yes. Then degree of u will be less or equal to degree of vk plus 1.
Degree of u
is less or equal to degree of vk plus 1.
Is less.
Actually, one thing we have to say, that there is no edge between the any two vertices of sk plus 1. Otherwise, S have to choose one vertex from that.
I didn't get this point. What are you saying?
Actually, if there is a edge like vi vj, where I and j are both less or equal to k plus 1, then S must contain one of those vertex. So then we will arrive at a contradiction. So we are assuming that there is no edge between them.
Between whom?
Between two vertices of sk plus 1.
There is no edge between two vertices of?
In sk plus 1. Because if there is any such edge, okay, then I have to choose one vertex. No?
Okay.
That we are assuming, since S intersection that sk plus 1 is equal to phi. Now, since degree of u is less equal to degree of vk plus 1, now sum over all degrees in n sk plus 1, and that will be less equal to sum of degree in sk plus 1. So that will be a contradiction.
Yeah, I think your proof is correct, but you use the fact which I never wanted to use on purpose. But your proof is correct, Soman. Okay.
So
Okay.
actually, sir, all the time, I mean, for any vertex cover should
Wait,
intersect
no,
this.
no, we are not going there, Soman. Okay, we are not going there. We have not reached there. Okay, don't use things which you know. Okay,
Okay.
I'm building from very, very basic things. Okay, have I used anything about all these special things that make those special algorithms at all in my
No,
lecture?
actually, that way I proved this. So
I understood, Soman. This is why I said that. Okay, let's not go there.
okay.
Okay. So yeah, he has a very valid proof, but like, okay, this is why I ask you people to, if you have a proof, send it to me. Okay. So I want you to think something slightly differently. I want to understand vertex cover as some very different kind of problem. Okay. Then I will make lots of other problems like that. Okay. So that is my whole objective. Okay. So let's, okay. This proof will not scale up, okay, when we go forward, okay. Suppose this is the case. What is the property, like very simple property, okay? What is the summation of this degree of V in S? Can anybody tell me? Here is an S.
At least k plus 1 times degree of vk plus 1.
No, I would say that this is at least this.
Yes, it will be. Yes.
Do you agree to this? Summation of degree V in S is at least E. Every edge is counted at least once. Maybe some edge is counted at least twice. So you can't be less than E. Right? If S is a vertex cover, so every edge is incident. So that edge is counted as a degree of some vertex, maybe after 2 vertices. So this can only overcount. It cannot undercount. Is this observation okay with everybody?
Yes.
Then we are done. Okay, I will show you why we are done. Okay. Okay. What is this guys? K guys. Top K guys. And where is my S? S is somewhere here. Okay. Now let's see. Summation. Let's call this set SK, because this is what we have been calling it SK. V in SK degree of V plus degree of Vk plus 1 plus summation W in S dW. Can you tell me what this number is? What is the first sum? What is the first sum? Okay, last sum is at least how much? Do you agree?
Yes.
Look, S, these, if you sum the degrees of these K guys in the red guys, and look, some of the vertices of in the blue, every vertex in blue has a larger degree than a vertex in red. Do you agree? I claim to you, if you can understand this, V in SK dV is greater than or equal to W in S dW. Is this correct?
Yes.
Because look, you are summing the degrees of K guys whose degree is less than the top, like least guy here. These are like numbers. 2. So if I told you I have K numbers where the least number is larger than your K numbers, then my K numbers is larger than your K numbers. No? Some of them is large because my smallest is larger than yours. That's it. Okay. So now, this is at least E. Now we don't have an isolated vertex. So this guy's degree is at least 1, right? So what did you get? Does it remind you something?
Sum of degrees is 2e.
Yes.
Partition lemma.
Yeah. So this is a contradiction. That's it. Look, when I ask you for exercise, I do not expect you to apply new things. All I expect you to apply is things which is them. So this is a contradiction. That's it. It's very simple. You cannot tell me that it's more simpler than this, right? I haven't used any fact. I said, look at these k numbers and look at these k numbers, right? Some of these k numbers is larger than some of these k numbers. So if this is equal to E, this is also equal to E, and then you added one more. Like, why did we look at high degree vertex? Because high degree seems to cover many more things. So if any is the only reason why this top k guys you are not picking because of some edges here and there. But in terms of how much they can cover, like at least number wise, they're as good as any k vertex. Right? Except some. And this is what. So what we have shown by observation, if there is a vertex cover of size k in J, or size at most k in G, then there is vertex cover S such that S intersection this is not equal to it. Okay? And I think this is a good time to take a break, and we will take it up on Thursday, 9:30, starting from here. Okay? So we don't meet tomorrow. We have no class, nothing tomorrow. I have to go somewhere tomorrow. So, okay? I like this night classes, by the way. So I might make it a, okay? Okay. Anyway, until you have any question, I'm done for the day.
Sir, recordings are available?
Yes, for my personal fun.
Oh.
Yes, of course, I'm recording it. So of course they are available.
So, sir, can I find somewhere?
Yeah, there is a reason why I'm not making it available, but I will try to get it up soon. I mean, I can, it's not, it just takes 2 minutes to upload it. Okay. Both my graph 3 lectures and this are recorded. But this time I just wanted you to have much more interaction in the class. And that is why I decided to give you video as a gift at the end of the course. But if there is far too much demand, I wouldn't, okay, I will release it. But like, that was my whole desire, that we make the class as interactive as possible, right? Look, I pause, I give you an opportunity to ask question. And if you don't understand something, here's a forum of people, you could talk to each other. That's also one thing that I don't want you to live alone and thinking, like catch one of these people and just ask them, discuss among yourself, no? That might be slightly better approach than listening to the same set of videos. That's just my feeling.
Yes, no, actually the problem is somehow I missed the class then. That is.
Yeah, so for those specific requests, I will give it to you. Sure.
Okay, sir.
But can I get the copy of this PDF? Like, I missed some facts.
Yes, Sonak. Yeah, this is like these kind of things I will give it to you. Sure. This is like lecture notes which you can have. So yes, I will send it to all of you people today.
Sir, any reference for this lectures, book or notes?
No, Kushal. That's unfortunate. Like there is a textbook for parameterized complexity where these tools are like in some form or other you will find them, but neither in the order nor the way I have tried to stitch them together. Okay, I've really made an attempt to teach you way more different than, look, if you want to follow textbook, there are 40 lectures on my homepage on these topics. You could follow them and then you can follow them together. That was done on purpose to follow books to a certain extent. But this time I decided to just try something different. So this is why I have, until now, I have just focused on one problem, and probably in my conceivable future, I'm just going to focus on this problem. Right? So at least problem-wise, you don't have to think about many problems. No, you know what you're going to talk today. Okay, Kushal. But if you don't understand something, Kushal, okay.
No, it's like after 2-3 weeks, if we want to recall any topic or details for that kind of thing, there should be some record. That's why I'm asking.
There are no books, but I will make the recordings open after 2-3 weeks, if that is helpful, Kushal.
Okay, sir.
Will that help?
Yeah.
Okay, I can send you what I write. This I will definitely do, because this is an important things to have something. Okay, so if you don't take notes in these kind of classes and you want me to send you this lecture notes, I will do that. So you don't have to worry about writing your notes. Okay, if you're happy with what I'm writing on my iPad, if you're happy with this, then I'm more than happy to share that with you after the class.
Okay, so this will do.
Yeah, 100%. Okay. So if we don't have any question, then good night. Okay, enjoy your.
I have a question.
Yes, Sonak, ask.
Yeah, so we didn't see any like the last two algorithms for vertex, or we see randomized ones.
Yeah.
But can we like there is any way to de-randomize those algorithms?
Yes, we will see those too. Time comes. We will do de-randomization. We will spend enough time on de-randomization. But now I want you to enjoy the beauty of randomization. Right? So I will leave. I mean, I want you to see how the simple algorithm could be powerful. That was my intention, right? But the moment I will start teaching you tool for de-randomization, things will become slightly messy. And when you will become more mature, I will teach you those. But yes, both algorithms can be de-randomized without even iota of extra running time. Okay.
Yeah.
Sir.
Yeah. Hi, Hemika. Tell me.
Can I get the recordings of the last two lectures, because I was not attending them?
Okay. So whoever needs some specific lecture, send me an email.
Okay. Yeah.
Okay.
Sure.
With those specific lectures, and I will make sure that you get it on time.
Yeah. Thank you, sir.
You're welcome. Okay. If there are no further questions, and so now we are moving toward deterministic algorithm. We'll make much better algorithms than these.
Yeah. Okay.
Much better algorithm than this. Don't worry. Okay. Good. Okay. Bye then. Good night.